Hi, today I've got a short problem for you, but it involves both friction and kinematics. So we haven't done a sample problem yet on kinematics, so I wanted to give you one that's a fairly easy one. So we'll have a good time with this one. The problem I've got, you're driving your car along a level residential street at 35 miles an hour when you see a ball roll out into the street in front of you. You slam on your brakes in case someone, like a kid, comes running after the ball. If the coefficient of friction between your car and the road is 0.67, how far do you travel before you come to a stop? All right, so our first step, always draw a picture. So let's do our picture. We're in a car, and the car is moving this way, and then ball rolls out into the street. And we were at 35 miles an hour, 16 meters per second. Okay, so there's our picture. Next up, knowns and unknowns. We're initial velocity 16 meters per second. That's how fast we're going when the motion starts. And our coefficient of friction between the car and the road is 0.67. That's all we're given. Okay, don't know how heavy the car is. We'll see what we've got. How far do you travel before you come to a stop? Okay, so that's our question mark, is how far do we travel? What variable is that? What can I call that for a variable? I could do delta x, I could do the change in position, or I could do x final. Both of those would work. So delta x, how far have we traveled? Let's just do delta x, yeah. So there's our picture, knowns, unknown. Next we have to choose what object we're going to do the force diagram on. Well, we have information for the car. Let's do the car. So I'm going to pick the car as my object. Force diagram. It's on level, so I'm going to draw my little box on the level. And what do we have? Well, what forces act on the car? We always have the force due to gravity, the earth pulling down on us, mg. We've got the road supporting the car, because if we just had that, we'd be free falling. Got to be something supporting it. So we've got our normal force acting up. And what's going on left, right? Well, we're slamming on the brakes and coming to a stop. So the car is moving this way. Friction's going to be trying to slow us down. So I would think that friction is going to be opposing our motion like that. Anything forward, and again, this is a tricky one, there's nothing pushing the car forward anymore. There's nothing actually making the car stay going forward. It's going forward because of Newton's first law. An object in motion wants to stay in motion. So I think we're done. I think those are all of the forces we've got. So the next step is a coordinate system based on the direction of the acceleration. Oh, that means we have to figure out the direction of the acceleration. Okay, if I'm moving to the right, I have a positive velocity, but I'm slowing down. And if you remember back in kinematics, we have positive velocity, and slowing down means the opposite sign for the acceleration. We would have a negative acceleration. So my acceleration is going to be backwards. And I can make that be consistent with this because left-right, I have an unbalanced force to the left, which means I should have an acceleration to the left. So both ways make sense. Unbalanced force tells me acceleration to the left, and kinematics tells me acceleration to the left. So that's the acceleration, which means we choose a coordinate system based on that acceleration. In this case, it's our standard one, plus x plus y. Next up, we're going to do our chart of variables. So xy chart for those three forces. So I've got the force of friction, that's one of them, and that's going to be going to the left. There's no up-down component, and it's going to the left, which is our negative x. So friction is a negative x. I got my mg force. mg, that's all in the downward, so there's no left-right component, and it's all downward, which is negative y. And the third one is the normal force. That's going straight up, no left-right component. Up is positive y direction. Okay, that looks good. So here's my xy chart. And is this balanced or unbalanced in the two directions? Well, in the x direction, it's got to be unbalanced because we have an acceleration. So x unbalanced. Up, down. Well, there's no motion up, down. The car is moving horizontally only. So it's not flying off into space or digging into the road. No horizontal, no vertical motion, so those had better be balanced. Great, I think we've got our system here. Next, we're going to do Newton's second law for the x direction, Newton's second law for the y direction. Sum of the forces in the x direction equals max, and add up all the forces in the y direction, that equals may. But we do have acceleration here, no acceleration here. These forces all have to be balanced, so the force net in the y direction has to add up to 0. At this point, what we're going to do is just add up the forces in the x direction. We've got them all listed right here. Well, that's pretty easy, isn't it? There's one force. Negative friction equals ma. That was very easy. In the other direction, we've got two forces. I've got a negative mg and a positive normal force. And I'm just going to set those equal to 0. Okay, this is a pretty straightforward one in terms of the forces. My two equations. All right, so we always end up with one equation in the x direction and one equation in the y direction. Now, what are we looking for? We're looking for how far we've traveled. That's a kinematics question, so I definitely have to do kinematics in this one. What is the only variable that connects kinematics with forces? It is the acceleration. That's the only variable that we can go back and forth between forces and acceleration, which means I need my acceleration. So how do I find my acceleration? Well, where is it in here? It's right there. My acceleration is there. I don't know the mass. Don't know friction. All right, what do I do? What do I do? Well, do I have any other equations that might help? That gives me a little reminder. I have a coefficient of friction, so I can use the fun equation. Friction equals mu times n. So if I'm looking for acceleration, I need mass and I need friction. Friction would equal mu times n. I have mu, that's a known, and look at that. I can get my normal force over here. So from this direction, I know my normal force is mass times gravity. All right, so let's see what we get when we slap those two together. I'm going to combine F equals mu n equals mg. Well, I guess 3, F equals ma. So this equation, minus F equals ma. Well, friction equals mu times n. Minus mu times n equals ma. But what's n? N is equal to mg in this situation. Don't forget that normal force changes. I'm looking for acceleration. I know mu, I know g, I don't know mass, but hey, there's a mass in every single term. Mass is gone. So my acceleration is negative mu g, negative sign. Don't lose that negative sign. It's important because that's telling us, reminding us, I guess, that the acceleration is in the negative x direction. And that's going to be important when we get to our kinematics part. So at this point, the forces section is done, and it becomes a kinematics problem. So how do we do kinematics? Well, you remember we have 6 variables to deal with. Initial position, final position, initial velocity, final velocity, acceleration, and time. So in this problem, how much do I know? Well, my initial velocity is 16. My acceleration I'll be able to get. And why don't we just make a calculation there? Let's figure out what that number is. It's negative 0.67 times 9.8. I get negative 6.57. So there's my acceleration. I now know my acceleration. Boy, this isn't looking good, is it? Negative 6.57. I need more information here. Okay, time. I know nothing about time. Do I know my final velocity? Well, yes, I do. How far have you traveled before you come to a stop? I come to a stop at the end. I do know my final velocity. 0. Okay, looking good. Our question is, what's delta x? How far have we traveled? And as I said at the beginning, you could have delta x be there, or you could say, what's x final? I'm going to say 0 there. And what is x final? We want to know how far we've traveled. If we set our initial position at 0. We're going from 16 to 0 meters per second, and we have a negative acceleration. We still don't know anything about time. So what's the only equation we have with kinematics that doesn't involve time? It's the squared one. V final squared equals V initial squared plus 2 times A times the change in X. I know V final, I know V initial, I know 2, I know A. I can solve it for the change in X. Woohoo! Got it. Anything 0? That's gone. So V initial squared equals negative 2A delta X. And I'm solving for delta X, so let's divide both sides by negative 2A. So my change in position is V initial squared over negative 2A. And if we put the numbers in, we get 19 meters. So we have traveled 19 meters to go from 16 meters per second, 35 miles an hour, to 0. Is that a reasonable answer? Well, 19 meters, you know, approximately 19 yards, 60 feet, 64 feet, you know, that seems reasonable. If you're coming to a stop from 35, yeah, 20 meters, 19 meters. I think that's a reasonable answer. We've got the right units. We've answered the question. The answer is reasonable. I think we've got it. All right, done with this one. Good job.